Okay, let's get started. So far, we have learned several different ways to exploit buffer overflow vulnerabilities in a program. We learned how to override the return address. If we are not able to override the return address, but we can override the safe frame pointer indirectly, we can still override the return address. So today we will start talking about several defensive approaches proposed in the last 2 decades to defeat buffer overflow. Some of them are already in all of our operating systems. Some of them are more theoretical, not very practical. We will start with those ones, then we talk about the practical ones. Then we also talk about how we can bypass those defenses. So even if they have been deployed in our OS compiler, they're not necessarily very, very effective. They can slow down attackers, but not necessarily stop attackers. So we're going to bypass them. So there are 2 main categories of those defenses, and we can call them the direct defense and the indirect defense. So the direct defenses, they tackle the root cause of the problem. They solve the problem at the very foundational level. They are good in theory. However, sometimes they can be very slow, very impractical, especially some research papers published in the last 20 years from programming language perspective and others. They're not necessarily practical. However, they can sometimes they are proved to be secure. Then on the other end, we have some indirect defenses. Some of them are very, very simple. Okay. So when you look at the idea, you would say, oh, this is very, very simple. They are not very effective. However, they are very, very fast. The cost is very low. That's why we are still using them right now. They are deployed in real-world systems. Several examples here. The very first, in theory, it's great. It's the base and bound check approach. This is a direct defense, and this is used in many other high-level languages like Java. Some of you probably heard about Rust. Rust is a different approach, which can be much faster. That's why Rust is getting very popular right now. It's fast, and it can prevent those kind of vulnerabilities. Other languages in the last 20 years, we use base and bound check, which it can be very slow. So that's why C and C++ didn't adopt something like this. Of course, there have been research to change compilers to adopt something like this, compiler and OS. Then we were talking about, today we're talking about stack Canary, which is also an indirect defense approach. It's a very simple approach. We just put some random number between the buffer and the saved EBP. So if you want to override the saved EBP or return address, you also have to override the random number we placed with. Then before we return, we check if that random number has been modified. So if that random number has been modified, it means someone has tried to smash our stack, right? However, it can only prevent those kind of sequential overrides. So the vulnerabilities we have seen so far, but there could be other vulnerabilities that can override arbitrary addresses, so we can skip those random numbers on the stack. Actually, we're going to talk about this Thursday. So today, the first one we're going to talk about is data execution prevention. It's called DEP. On some architectures, it's called the non-executable, NX. Some call it write, inclusive, or execution. So they mean the same thing. So this is also an indirect defense approach. It can prevent executing share code on the stack. So previously, we put share code on the stack. and we execute the data, the shellcode on stack. The rationale here is everything on stack should not be executable. Should just be data, should be no code there. So why do we give permissions to anything on the stack to execute? That doesn't make sense. So let's first look at the base and bound check approach. This is a spatial. So here, so far, we have been talking about spatial memory safety. Okay, we're overwriting something. That's a spatial problem, right? So it's not a time or temporal problem, which we will discuss later in the second half of the class. So let's say we have a pointer A. From C developer's point of view, you have a pointer, you have a char star A, that's a pointer. So associated with that pointer, we should always have a base address and its bound. Its lowest address and its highest address it could point to. So developers do not necessarily come up with those two pointers. The compiler or OS can instrument those directly. Prepare. So let's say we have a pointer A, and we use malloc to allocate some. This is like 512 bytes, and then assign that address to A. Then implicitly, so then we will also create a base and a bound for that A pointer. And the A base will be where A is, in this case, the A bound will be A plus 512 because we only allocated 512 bytes. We should not be able to access beyond that, right? Then only access between this range will be allowed. So at the SQL level, if you do this kind of access, A0 to A511, that's okay, right? The program will allow you to do that. But if you do something like this, you'll try to access A512 or A-1, the program will not allow you to do that. But the standard C code do allow you to do any of those, okay? So here, the compiler will change the program to instrument some checks, so those kind of access will not be allowed. So if there is another pointer B and A is assigned to B, then obviously B should have the same base and bound. If for more complicated cases like this, we have B and we're accessing one element of B and we're assigning that element address to C. In this case, C still should have the same bound. Okay. But to implement this propagation, obviously there are some very complicated rules. So the overhead of this approach is actually very heavy, as you can see. For every pointer the developer creates, we need to have two more pointers, two more variables. So the program size is getting bigger. Then for an assignment, one pointer assigned to another one, we actually assign two more. The programmer didn't write this part, the compiler instrument this part, or the hardware can do this. So, so those two times overhead here. For any access, we need to add some comparisons here, whether it's the access is higher than the base and also smaller than the bound, right? So the overhead of this is actually quite big. There are several papers talking about this approach and also try to optimize here and there, but fundamentally you can say the cost will be high. So this is a paper published like 15 years ago to establish this spatial memory safety for C code. The same team actually published another paper at the same year using a hardware-based approach to make things slightly faster. Maybe faster, much faster than software-based version, but it's still the overhead is still high. So that is an approach that is absolutely secure. However, the cost is too high. That's why we're not really using it. Then another approach to make it safe is the Rust-based approach, compiler-based approach, not compiler-based instrumentation, but compiler-based analysis. And at the programming language level to forbid those insecure use of pointers. So we're not going to talk about that today. Instead, we will talk about several other, today we will look at two defenses. The first one is data execution prevention. So all of your phones, all of your laptops already have this feature. So this has been there for maybe 20 years. Like I said, several names for it. It could be DEP, data execution prevention, or write inclusive execute. Means if a memory region is writable, then it should not be executable. Okay? For example, the stack. Stack is writable. So anyone, if you can exploit the buffer overflow, you will be able to write something to the stack. Since it is writable, it should not be executable. The code section loaded by the loader is readable, it's executable, but it is not writable. You cannot write the code in that section. Right? Also, at a CPU level, the feature probably is just called the NX, non-executable. It's just one bit in the memory management unit. So to understand how this works, let's revisit the conditions we depend on to pull off the attack of returning to share code on the stack. To return to the share code on the stack first, we should be able to put the share code onto the stack, right? Including environment variable or command line arguments. We are putting share code onto the stack. Then the stack should be executable. Then we need the ability to override one return address before the corresponding return instruction is executed. Also, we learned last class, we can override the saved EDP to obviously, we want to know the address of our destination, the share code, but we can create a huge knob select to lose those requirements. So this feature of data execution prevention is taking out the second condition here. We're making the stack not executable. This is not a perfect solution, but it can slow down the attackers. Actually, this approach was very effective for many years before new attacks were discovered back in maybe 2009. So this approach was discovered in, this approach was proposed in maybe early 2000. So also you can see why I'm listing those conditions here. So if you are a security researcher, you want to come up with some approach to defeat or at least to slow down attackers, you just need to list those conditions. So take one condition out, then you can come up with one approach. Not necessarily a perfect approach, but it will be able to help. And sometimes you don't know. When your perfect approach may not be perfect in terms of performance, in terms of a cost. So they are not really practical. Imperfect approach, which seems very, very naive, actually will be deployed there for 20 or 30 years and really make real world impact. So the idea of separating execution, the permission of execution and read is actually not new. This can date it back to the idea of the Harvard and the von Neumann architecture. So most of the computers we use right now, it follows this von Neumann architecture, which means the same memory or bus are used to store both data and instructions. that run the program. So there is one channel that we get both data and instructions from. Okay. So at least at the hardware layer, most of our computers are designed that way. Some of the computers are not. Some of the microcontrollers, they separate different regions. This region is only for code. This region is only for data. Of course, in our computers, we have .data section, we have .text section, but the hardware layer, they are on memory, right? So the memory actually stores both data and instructions. So another architecture or paradigm is a Harvard paradigm. In this paradigm, they store machine instructions and data in separate memory units. And they are even collected by different buses. Like I said, some microcontrollers I have seen, they adopt this architecture, but not many. So most of the computers we are using is the von Neumann architecture. The fundamental problem with the von Neumann architecture is there is a channel sharing problem. Data and instruction, they share the same channel. So when you fetch from that channel, you don't know you are fetching from you're fetching data or you are fetching instructions, right? Fundamentally, that's a problem. However, because they share the same bus, they share the same memory, it's cheaper to implement something like this. So older CPUs, kind of around 2000 or even before that, they do not have that execution permission explicitly defined in the system. So there is only read-write permissions. So read permission implies execution permission. So now we have read-write execution. Then we even have memory regions that is only executable, not readable. Okay. So before we only have everything readable. If it's readable, it's executable. Later we have readable and executable. Now we have memory regions that are only executable. So the use case for that is for the IP protection of some code. We want to execute that code. However, we do not want to disclose that code to anyone else, right? We want to protect the IP of the owner of the code. So the CPU will support it's only executable, but not readable. So AMD 64, they introduced the NX bit back in 2003, and that introduced the non-executable bit. So that will be one bit in the permission of a memory page, and that it will be honored by the memory management unit (MMU). The Windows and the Linux started. So after the hardware feature was introduced, Windows and Linux started supporting that in their OS back in 2004. So it has been 20 years. So now, if you on our server, we use Linux. If you compile a program, by default, the program, the compiler will say the stack is not executable. So far, the programs you have been hacking, you are able to return to the shared code there because we explicitly used this compiler parameter or compiler option, which is dash the executable stack. We explicitly tell the compiler we want to make the stack executable to disable this protection. So, for example, we have two programs. This program compiled using on the same system compiled. The only difference is one of them we're using that dash z executable stack flag. Another one is no that flag is default. So the default one you can say is this one. You can say the L file, is marked as this memory region stack. It's readable, it's writable, but not executable. But this is only in the L file. Okay. The operating system actually needs to honor this. The operating system will load this program into memory and read those permissions the program is asking for. The operating system needs to honor this. We'll actually set the memory of that stack as not executable. The same thing for, so here is the executable version, and you can see this one in the L file is marked as executable. So the OS, the loader will honor that, will make the stack executable. So you can see there are two steps. The first step is the compiler mark the L file. The second one is the OS or loader will honor the marking in the L file. So in one of the competitions we participated in recent years for microcontrollers instead of those Linux systems, we find out that many teams they were using the non-executable stack feature, which means the compiler programs like this. So in the L file, it says the stack is not executable. However, for those microcontroller systems, there's no OS, there's no operating system. So no one is there to honor this setting. So many teams, they thought their stack is not executable because they only finish the compiler part. They never implement the bootloader or what system configuration part. So it was not honored. So what can DEP prevent? Obviously, attacker can still corrupt the stack. The attacker, you can still override the return address. You can still override the saved DEP. You can even put the share code onto the stack. You can still do that. It's just you cannot execute that. Okay. So when the EIP register points to the stack, because the stack memory region is marked non-executable, you will get a segmentation fault or some other CPU fault. So how do we bypass this? It's actually quite easy to bypass this. And we have already learned how to bypass this last week, actually. So back in 1997, there's a hacker called a Solar Designer. If you Google, you can find his brilliant. So this guy come up with an idea called return to libc attack. And this attack can bypass a DEP. This attacks, but there are other security features to make it not as effective as before. But with what we're going to learn later in the class, return-oriented programming, we will be able to expand return to libc to a more general form that can do all kinds of things. So the idea of return to libc is very simple. The C library already includes all kinds of useful functions. Some of them are very powerful. Right? So in the previous weeks, I included that print flag function in the address space for you. So as long as you jump to there, you can print the flag. The C library obviously doesn't have a print flag function for you, but it has some other very powerful functions. For example, there is a system function. C library has a system function, which will create a little process, whatever you want. Okay. And the system function takes a string as input, and that string is just a command. For example, you can do bin sh, then you can get a shell. You can do cat/flag, then you can do that cat. The same as what you are typing in a terminal. So the idea here is very simple. instead of injecting some shellcode, instead of returning to our shellcode, we return to the system function and put one parameter there. Okay, the parameter will be the share or just a command, right? And you already learned how to do this, right? We already learned how to return to any function and with parameters. The problem here is on our current server, this will create a new process. Same as our shellcode, when we create a new process, it will drop the privilege. So you will not have the root privilege. It will be CTF user privilege. So to keep that privilege, what you need to do is you need to call set RUID first, then call system, right? Or return to set UID first, then return to system. But we also learned last week to return to multiple functions. It's actually not easy to do so, right? Because their return address will be next to each other. However, that return address may overlap with other functions parameters, so it may not work. So right now, we do not have ability to return to set RUID because set UID takes two parameters. If the set UID doesn't take any parameter, we can do that. Then return to the system. We do not have the ability to do that right now. So the second half of the class, after we learn how we do ROP, return-oriented programming, we will be able to do that. So today we're going to show is directly returning to system, but we will not be able to get a flag. We will only return of the user CTF. So this is the program we're going to hack. This is the same program. This is the same one. We took a look last week. The main function calls vol_foo. After that, it calls IPD the pool. Vol_foo has a buffer. Then it uses gets to get input from std in. So obviously there is a buffer overflow here. The difference here is for this program, the stack is not executable. The program is the same, only the way we compile it. This one is the stack is not executable. So if we go to this, one. So if we do a read L, let's see. Here. So we can say this version, the stack is not executable. Okay. So even if you put shellcode there, you can try. I'm not going to demonstrate that in the class, but you can try use the same shellcode you used in last class and try to hack this one. It will not work. If we take a look at the other version, which is okay, just this one, Overflow return 4. If we just go to Overflow return 4, we will read else. Maybe. And you can see the stack here is executable. Okay? That's why you were able to do the attack. You did the last one. So for this one, we are going to use the return to libc approach. We will be able to get a shell, but not necessarily the root shell here. So this is what the exploit looks like. We're not going to redo the calculation. Okay, so the garbage, we try to fill the buffer, and the saved EVP in total is 52 bytes. After that, we are going to override the return address. But this return address will not be our share-code address. We don't have a share-code there. This address will be the function, the system function's address. Okay, so that function is in DeepSeek. On our platform, the easier way to get that address, you just debug this program. Then symbols are loaded. Then you just use p print to get that address. Now after that, you need 4 bytes of another garbage. If you remember what we did in the previous class, we return to print secret with a parameter. Then you will know why we need 4 bytes of garbage here. Right? So after that, that will be the parameter for the system function. And system function parameter is a string, and that is the command we are going to use. And in this case, the command we are going to use, the first thing we are going to try is just dash bin sh. Okay. So where do we put this dash bin sh? We can put this anywhere, okay? Because this is not code. This is just down, right? This is not executable. This is just a string, right? So we can put them on stack. There are other places we can look for this string. Actually, the C library itself has this string already. So as long as we can find the string, which is already there, we do not even need to inject the string there. Right? So let's try this first. So we can debug this program. We set a breakpoint at the main function. We run this program. Now this program is executing, which means the C library is already loaded. So if we just use p run system, it will print out the address of the system function. And this function is in DeepSeek, okay? __ DeepSeek _ system. So this is the address of this function. The next, we want to look for a string like bin sh without, yeah.
Would the address of this change on a future run outside of GDB?
Right now it will not, because we disabled the ASLR there. In short, it will not. For this challenge, it will not. So because this is code. So previously for the environment variables, they're different because that's a stack. You push different things to the stack. Here, the code part is always it's not changed.
Yeah,
right? So it's much more stable there. So we want to find the string bin sh, right? And I already told you that the C library actually has that string. So usually we do info address, info which one? Like info files. So there's a command called info files. It will tell you different program files modules where they are loaded. Let's say here, this is the interpreter is loaded here, and that's obviously a code section. And there are other sections we learned before, like elite, PIT, they are loaded in different memory addresses. So this is one kind of address. And we actually have, there may be multiple copies of that string, but I just know there is a copy in the C library data section. So where is the C library? Looks like this is the C library data libc. Yeah, maybe this one. So you can say here, this is the libc library, and there's .data section. We can try there. Maybe it's there. Maybe it's another section. So let's try this address. This range. So in GDB, we can use the find command to search for some values in the memory. So the first parameter is the starting address. The second is the ending address. Then you can. The third one is what you want to search. We want to search for the string bin sh, right? So we do this command. We do not find this, which means this is not the address we're looking for. What else we can? So this is data. Oh, here, this is read only data. I think it's more likely to be here, right? The string is the string should be a read only data. You don't really change the string. So let's try this again. Okay, we do find one. We do find that string is there. We can examine this by X command. Using X command, exam one string, one S from this. From this memory location, and you can say, at that memory location, we really do have a string. Maybe there are other useful strings. Let's maybe examine 10 strings from there. Yeah, you see, there are other strings there as well. But somehow it has a string we want. Then from those addresses, where's system again? Okay. Now we have system. So from those two addresses, now we can write our exploit. Use Python 2 to do this. 2. So we need 52 bytes of garbage. Then the return address in this case is system, the function system's address 30, 38, E1, F7, right? So if we just do this, we will be able to return to system, but there will be a garbage pointer there. It may give us a segment 4. If it doesn't give us segment 4, it will treat whatever is there as a command. Then it will give us invented command or whatever. Oh, forgot to type. Type this. So we do get a segmentation for it. So after this, we need another 4 bytes of garbage. Now after this, we will have the address of the string bin sh, which is 52, 5203 F6 F7 F6 F7. Going to this. Where did I do wrong while we're getting a segmentation? Does anyone identify a problem here? 30, 33, U1 F7, 52. Really? Oh, we forgot about the cat, right? We forgot about the cat. That may be a problem. Then eventually it will. Let's try. Oh, it works. Okay. Want to do this? We do get a shell. However, where am I? It was a gap shell, not a root shell, right? So if obviously if we change 1 byte, it will not work, right? When we change 1 byte, we do not have that slash in this case. And it should not. Oh, without that slash, it works. Okay. Without that slash, it works. That's because we are, without that slash works, because right now we are in the root folder. But if we add one more, then this should not work. Wait. For this, the system function was returned to successfully. However, it's trying to execute this command, insh, and it couldn't find this command. Right. So if we do this, you will not trigger segment 4. So this is how return to DeepC works. Let's try another approach. So here we're trying to get a shell. Instead of getting a shell, let's just try to do a cat flag. Okay. It's not going to give us a flag because we don't have a permission, but even to make this work, we need to think how to make this work. So what's the idea here? First of all, do you think we can find the string cat flag in the address space? We were able to find this string in the program, but how about we find this? Chance is very low, right? Yeah. So if we cannot find this string, what do we do? We just inject it in the thing, environment variable, whatever, right? So that's easy. Then another issue is we need to know the exact address for this. What if we do not know the exact address here? So previously, there was one example where we're trying to use a flag, right? Just a flag. So we put a lot of slashes here, // right? Because they are equivalent to just one. So in this case, there is a command before that. And then before the command, we cannot put slash. So what can we do to put some kind of padding here? Exactly, right? We can put a white space. We can put a long white space there. So we do not know, we don't need to know exactly the address of that. So let's try this one. We'll do what else? Export, which is the string. So we put some white space. Let's put 500 of them. Now after that, we will be what? Cat flag. The // here doesn't really matter because we are in the folder. Let's say this looks correct. Right. So if we print environment variable string, we can say that is our string. I have a lot of white space. Okay. The reason for this works is if we do a cat flag, obviously permission denied. If we have a lot of white space here, it will be the same thing, right? Or we can even put a lot of this one here. So now we have that string there to get environment variable 32 string. I have this address. We will use a similar exploit. So this part is not changed. This is the address of the system, not changed. This is the address of the string. This string we need to change to where our string is, ff dd. So we have 500 of white space there. So I can safely change that to de. Then 5 should be it. Let's do this. Okay, that's successful, right? We were successfully executing the cat flag command. It's just we do not have the permission to do that. So this one we do not get a shell, so we have anything to get a segmentation. So you can see that to really get the permission of root here, before we return to that system function, we need to return to that set RUID function of what we did in the shellcode. We change the effective UID again. We don't have. So right now we don't have the technique to do that. We need a return-oriented programming technique. Okay, so you can say that. So the conditions. So this return to libc attack doesn't need the condition to inject the share code there. It didn't inject share code. It doesn't lead the stack to be executable. So from attacker's point of view, their requirements are fewer. They are able to do more attacks. So that's why this is harder to defeat. So far, we have been saying many different attacks, and all of them can fall into the category of control flow hijacking attack, right? Eventually, we overflow the return address, and that return address is actually a pointer to a code. Okay, so it's a code pointer. From C code point of view, it's a code pointer. And that code pointer is used later by the CPU, which means the CPU will resume execution at that place. And because of that, we hijacked the control flow. The CPU is not running what it was supposed to run. It is running some code we put there or running some code, even if we didn't put it there, but it's not supposed to be that kind of control flow. So that's why it's called control flow hijacking. And in control flow hijacking attacks, so far we have seen two different attack types. The first one is called the code injection attack, in which we inject the malicious code or share code, then subvert the control flow to eventually execute our malicious code. And the malicious code, usually we call it the share code, and supplied by us, and their machine code. Another type, which we just saw, is the code reuse attack. As an attacker, we didn't inject malicious code there. We didn't inject share code there. We only try to reuse what is already in the address space. So we tried to return to print flags. And just now, we try to return to system, return to other C library function calls. Later, we will learn how to return to other places. That's called return-oriented programming, which you can consider it's a more general version of return to libc attack, which is very, very powerful. You can see the return to libc attack right now has limitations, right? We are not doing arbitrary computation with this one. We cannot even get the root shell there. But after we extend that to return-oriented programming, we will be able to do whatever we want. So in both cases, the attacker's goal is to execute arbitrary code, take full control of the victim's machine. And attacker eventually needs to alter a code pointer. The code pointer could be a return address, could be a function pointer. So far, we haven't showed cases with function pointer, but we will see later. Then what kind of code pointers we have? So far, we're only overwriting the return address, but there are many, many different code pointers in the address space. That's why the attack surface for attackers is huge. there are many things attackers can do. On the stack, there are function return addresses. Also the free pointers, we change that. Long jump, there's a C programming feature, set jump, long jump. There will also be code pointers. The heap may have complicated data structures. Those data structures may include function pointers as well. For example, C++ has classes. In C, there is no class. In C++, there is class. In each class, at its lower address, it has a V table, the virtual function table, and it has many different functions. Right? So those are function pointers. If you change one of those function pointers, then later call that function, here, you can run arbitrary code. Or other sections, they may have code pointers as well. So even if we cannot override code pointers, we just override data pointers, we will still be able to hack. But I don't have very concrete examples today, so we will skip it. So the second difference we're going to talk about is shadow stack. This is also a very effective approach, and this is related to another concept we will study later in several weeks. It's called control flow integrity. So in control flow integrity, we have a program, and we have a defined control flow for that program. We will say for this program, only function A calls function B is legal, function B return to function A is legal, function B return to system is not legal, something like that. Right? And shadow stack is actually a part of that control flow integrity policy. It's for the backward edges. The backward edges means returns. The forward edges means calls. The shadow stack, so far we haven't been talking about the forward edge, so we'll talk about shadow stack first. The idea of shadow stack is very simple as well. So let's say this is what our stack looks like when we have multiple function calls, right? So we have function R1 calls function R2, R2 calls R3, R3 calls maybe R4 functions. So the stack will look like this. So R1 has its own function frames, stack frame, which we are already familiar with, which has parameters to R1. Then the return address to R0 is part of R0. Right? Then we have the saved EDP, right? After that, there may be something in the between. After that, we have the second function, the R1, R2, the R3, R4, right? So this is what we are familiar with. The reason we have this buffer overflow vulnerability is one of those functions is vulnerable. It has some using some weird functions like get, string copy, those kind of things. And by exploiting the vulnerability of those functions, we will be able to override the return address or save the EDP, whatever here, right? So the idea of shadow stack is very simple. The attacker is only able to override whatever is here, okay? Then we create another stack. We reserve another memory region to make another copy of those return addresses. And that new memory region, we call it the shadow stack. There are two popular implementations of shadow stack. One is the traditional one. So you just store the return address and you store them one after another. Okay. So you save a lot of space. Another one is the parallel shadow stack, in which you still only store the return address. However, there is a constant offset between the return address on the original stack and the shadow stack. The benefit of this is it will be much faster. However, you waste a lot of space. And we're going to look at how this is implemented. So this can be implemented at the compiler level. So say code developers do not need to do anything special. The compiler will automatically do this. Let's say this is what is in the traditional channel stack approach. This is what instrumented to the program. Let's say we have a channel stack. As long as there is a stack, usually there is a pointer, right? Stack top. In this case, obviously, we do not have a register to do that. For the main stack, we have a CPU register to store that address, which is ESP. In this case, we don't have a more register to do that, so we just use 4 bytes of memory as the pointer to point to the top of the stack. And that 4-byte address, we use GS 108. So this is actually a memory address for this. Then when we are pushing something, when we are making a function call, we are pushing the return address to the original stack and also to the channel stack, right? So what we do here is this 4 instructions will be at the top, but at the very beginning of your program, of your function, even before that push DEP stuff. So we will first get the shadow stack pointer to register EAX. So this one is AT&T syntax. So the second parameter is the destination. We are moving this to this. Then we are moving what ESP points to ECX. I already told you this will be instrumented at the very beginning of the program, right? The function. So what does ESP points to at this point? What? Which is what? So this is directly after the call instruction, actually. Yes, so the ESP in this case actually points to the return address. So we are copying the return address to the register ECX, then copy from ECX to where the shadow stack is. So that's it. We are making another copy of that return address at a different location. And we assume that location is safe. Attackers cannot overwrite that location. Obviously, that assumption may not always be correct. Hackers may have other ability to override that, but this is another indirect approach to make it harder for the attacker to pull off the attack. Then when we returns, this is the return, okay? So when we returns, we will check whether the main stack's return address matches with the shadow stack's address, right? Or in other case, we assume the main stack address could be overwritten, then we directly use the shadow stack address. Let's say this piece of code, what it's doing. So it will first copy the shadow stack pointer to ECX. Then we're trying to load whatever the shadow stack pointer points to EDX. Then we move that to where ESP points to. So in this piece of code, we're just copying the return address back from the shadow stack. We do not really care. We do not even check whether the main stack address was overwritten. Right. So this is a traditional channel stack. Obviously, another approach is you do not directly blindly use that address. You check whether they match. Right. You get that shadow stack address, then you compare whatever you get from the shadow stack with your main stack. If they do not match, it means the main or the shadow stack has been overwritten, then we just abort the program. That's another approach to handle. This is about the handling one. Yeah. The compiler will instrument those instructions there. Yeah. So for developers, you don't need to do anything. Yeah. The C code is not changed. But the compiler will instrument those instructions. Compiler do all kinds of things that you don't know, obviously, instrument all kinds of code. So let's say the overhead here is actually quite high. There are many more moving instructions, memory reads, memory compare, and also conditional jumps. So another approach, the parallel channel stack, you will say the overhead, at least the instruction overhead is much smaller in this case. You can say the first one, the prologue for parallel channel stack, we just put, we are still making a copy of the return address, right? And we just use the pop instruction to do that, because the pop instruction can actually move from memory to memory. And the pop instruction will have a fixed offset. That's a distance between your main stack and your shadow stack. And we just pop whatever DSP has to the new memory location. So we're making a copy of the return address, but because this is a pop, we need to subtract 4 to ESP again. So only 2 instructions. So previously like 6 or more instructions. If we just want to copy the return address from the shadow stack back to the main stack, also just 2 instructions. So much shorter than before. Exactly. So, but the attacker needs some other abilities to do that. So here, let's say if you just have a gets, right? The vulnerability here is a gets, a string copy. You are able to overwrite the shadow stack, but you are able to overwrite the main stack. But you don't really have the ability to override the shadow stack, because the shadow stack may be in .data section, but not necessarily on the stack, right? Yeah. But you are right. This is not a direct approach. It's not direct defense. There are many ways to bypass this. Yeah. I don't understand why you're subtracting from these. So do you understand the first instruction? Whatever the return address to that you want to just pop it to that. Yes, but what is pop? Pop implies that you add 4 bytes to ESP, right? So after you execute this instruction, ESP will not point to the return address again. Yes, that's why you need to subtract 4 to that. That is the main stack. You need pointing at the direction. So this one will not be changed to the register, will not be changed to where shadow stack is. It will just increments 4 bytes. That's it. Because this is a pop, right? Because this is the instrumentation. After this, without those 2 instrumentations, ESP should point to the return address. So after those, ESP still should point to the return address. That's why we subtract 4. So a paper published several years ago, they measured the shadow stack, and the measurement is roughly 10% overhead for traditional shadow stack. We're talking about the performance overhead. For parallel shadow stack, kind of like 3.5%. This shadow stack is just for the control flow, right? But you can override local variables. Yes. Yes. Yeah. Okay. So that's the 2 defenses we will discuss today. So for the rest of the class, we still have like 35 minutes. So for the rest of the class, today's class, I want you guys to finish the challenge we started last week. If you finish that, there are two more challenges. So first, finish the Behemoth one. If you finish that, then finish on our server, reverse engineering 3 and reverse engineering 4. Okay. So I will be there to help you guys, and they are also in this week's homework. This is the homework of this week. So Behemoth is something I didn't demo in the class. And also Overflow return 8 is not something I didn't demo in the class. There's 32-bit version and 64-bit version you need to finish. After that, you need to capture the flag of two reverse engineering challenges, reverse 3 and reverse 4. After that, there is a bonus question. There is a harder version of Overflow return 8. It's a harder version. It's from the same source code. However, that version is harder to crack because we use a different compiler options. So if you finish that, you get some bonus points. So how many of you already got Behemoth? What? Oh yeah, I remember many of you were very close last week.
Got my notes for that.
Okay.
And then didn't go home and finish it.
Okay, cool. So this week you have to finish it, part of the homework. Yeah.
I've read so many times. I just looked at that. And then H F W F U F U R U. Kind of J W and last time I looked at, I was trying to get it early, but it's pretty sure I've got it in fine. The copy of that, right? I didn't copy that, didn't have anyone with that, so I'm trying to save it in. The reason that I saw it last time is that it just loads me so much that I'm thinking I've not read next since. Is there an alternative PowerShell I could be finding that would let me access APM? Yeah.
This one is not creating a new process. You didn't create a new process, you didn't make yet you can do it. So you have spirit in the process. Yeah. That process has been created. Next, and against it.
Yeah. Did you use the HAHF?
That's different. Yeah. But you have 54, but that's important not.
No.
That's it before you know it. This part out.
Where did you find that other one?
Yeah, it's there on the take home.
Oh, electric stack. That is different. Yep. Oh, no, I've typed it in probably 2,000 times by now. Oh, yeah.
The program you are having, where you are. You are keep having.
I did it, thank you. Yeah.
But here's your code. You cannot recognize it because which one is on the other bank. No, that's the thing with no bank on.
Oh, right, sure.
If you want to use this one, then you change the screen, the plan how it can. You can use this one. Never say that. I'll say change it. You can hear from the video.
These after an L5 is old. L5 slide is old, L6 had a different password.
Okay. That should be, oh, L5, I did put it, L5?
Yes,
Should be L6. L7, or L7. Oh, yeah. Sorry about that. You got to change your password every year. Ah. Got it. Yes. Yes. Yeah, for some reason it's not overriding. And because it's usually override the. Why, this is 43 and a half, so. Yeah. Yeah.
Formulating what I can do. If I could walk you through what I'm
Yeah,
thinking now and
sure,
see about the
sure.
analysis.
Yeah.
So I'm thinking return to shelter here.
Okay.
And so what I'm looking at right now is that when I'm examining the
Mhm.
I see that I believe we are starting the buffer that we're filling into at EDP minus 43 half, which is 60%.
Yes.
So I think that I can get over buffer as well as the EDP.
Yes.
So that much garbage.
Mhm.
Then I can overwrite a new red pointing towards an on slab that I put in, followed by the shelter.
Yeah.
And I'm thinking I can just put that in immediately after the red.
Oh, you mean we just put it
Yeah,
there?
put it in the stack above.
Yeah.
Okay.
As long as we can.
As long as I can find that,
That address.
which I'm thinking I can find just
Yeah, the probably.
EDPing,
Yes.
if I have a big enough
Okay,
output.
Yes.
Okay.
That makes sense.
Great.
Yeah, you can do previous to, yeah, because X means right? So usually with dollar sign, so we dollar sign. Yeah, dollar sign is really good, yeah, because you're doing wrong now, right? You did? No, you didn't wrong now, the R, yeah, R.
Thank you.
Just set a breakpoint.
Yeah, oh, I did that, and then forgot to run.
Yeah.
Thank you.